Okay, welcome back from break, everyone. It totally was not long enough, but I hope you're at least a little bit refreshed. Before we get started today, let's put up our schedule. So here's where we are today, October the 11th. Our test is next Friday, so like 9 days out. I don't have the test made up yet, so I can't give you the details about it. I'm hoping I'll get it written between today and tomorrow. Some people have already asked about the cutoff for the test. I don't quite have that decided. It'll probably be sometime in Friday's class or early Monday's class. When we get to it, I'll let you know, and I'll put information up on Brightspace. A couple of reminders about the test. I did say that you were allowed to bring in a sheet of notes, so that may help you as you're getting things ready. And please make sure you bring a calculator. A lot of times students don't bring a calculator. If you don't have one, you won't be able to finish everything, so make sure you have one. I don't care much about what kind of calculator you have, as long as it doesn't have Wi-Fi access. Okay, so a graphing calculator or whatever, that's all fine. Just not the fancy pants ones. The test could be conceptual questions or problems. Either is kind of fair game. Pretty much anything we talk about in class, including proofs that we do, any of those things could go on the test. So you should be reviewing your lectures pretty carefully to get ready for the test. So before we get going today, any questions? Oh, and we are going to write the test in room 2038, just up from your lab. So your lab is 2039. We're going to write in 2038, the room next to it. There's a little bit more space, and we'll be able to spread out there a little better. And I'll get that up on Brightspace as well for a reminder. Okay, so no questions? So we did a lot last time we were here. We talked about the electric field around a capacitor. We talked about electric field lines around some distributions of charge. We talked about the idea that if we know the electric field lines, it can tell us something about the charge inside of a surface. That led us to think about a quantity called electric flux. Electric flux gives us an idea of how many electric field lines penetrate a surface. We decided that it depended on the electric field, it depended on the area, and the relative angle of those two things. And we defined a Gaussian surface. So today we're going to get to our mathematical definition of electric flux. So we'll write down an equation. Okay, so, actually, why don't I just kind of pop this back up. This was the very last slide we did last day, and we said for electric flux, we showed how it depended on all the things. And the last concept we talked about was if we had a tilted surface, we see that we get the same number of lines through this tilted surface as we get through the perpendicular projection of the surface. So the lines cut through the perpendicular bit, they don't cut through the parallel bit, and through the perpendicular bit is the same as through the whole surface. So we're going to work with that concept today and coming up with our definition. So we want to get an expression for our electric flux. We know it depends on electric field, area, and angle. And our electric flux is a measure of the number of electric field lines penetrating an area. So our electric flux, we know, depends on the size of the electric field, the size of the area of the surface, and the relative angle. And when these two come together, we know it depends on the perpendicular part of the area. So that's where the dependence is going to come in. If a surface is perpendicular to the electric field lines, like it is in this picture, so these arrows are the electric field lines. This is a 3D image of our picture. This is our side view. Our area, we know how to find an area. It has a length L and a width W. So for this area, there's our length L, there's our width W. In our side view, the length is into the page, the width is this length. If we wanted to find the area of that surface, we would just do length times width. Okay, I think that one's not confusing for anybody. Once we get our tilted surface, now's where we have to think about, we need the perpendicular bit, because the number of lines through the perpendicular bit is the same as the number of lines through the whole surface. So here's our 3D image. It's got the same length L. It's got the same width W, which we can label on the 3D picture, or we can label on the side view, W. It's the perpendicular projection of W that matters. So right down here, we can draw the perpendicular length and call it W perpendicular. And on our side view, it would be this length right here. And this would be the parallel bit. And all of the lines that cut through the surface also go through the perpendicular bit. Our surface is tilted at an angle theta. We'll put our angle theta in here. So now we know that the flux depends on the perpendicular part of the area, so the area of this bit in here. Let's find the perpendicular bit of the area. So we know that the area of the perpendicular surface, the area perpendicular, is going to be the length times the width of the perpendicular surface. We can find the width of the perpendicular bit, this bit, just by using some trig. That's a right angle triangle, that's the hypotenuse, that's the adjacent. We know that the length of this side that we call W perpendicular will be W times cosine theta. So that's some of our basic trig. So our perpendicular area is the length times this perpendicular width. The perpendicular width is W times cosine theta. So L times W is A times cosine theta. So the area of the perpendicular part of the surface is the area of the regular surface times the cosine of the tilted angle. Okay, good to there. For our electric flux then, this is what it depends on. Our electric flux now, we say is, so that's the capital letter phi with a subscript of E. I think we went through that last time, E for electric flux. Depends on the electric field E, depends on the perpendicular area, so it's E times A perpendicular, or E times A times cosine theta. Those of you who have done some linear algebra, either in high school or in Math 2050, might recognize this as the scalar product, E dot A. So there's our definition for electric flux. It's the scalar product or the dot product between electric field and the area of the surface. Any questions here? We are going to go through scalar product for those of you who need a refresher. So this is the equation we're going to be using for electric flux. We'll start going through some examples. So let's do a quickie review of scalar product first. So a scalar product is sometimes called a dot product. It's a way of multiplying two vectors. So we do, if we want to take the scalar product of A and B, we say A dot B. The dot is really important. You can't leave that out. So you got to have the dot in there. The main deal about a scalar product is you multiply two vectors and you get a scalar for your answer. So when you do A dot B, your answer will not have direction. So your answer will be a scalar. Two ways to calculate a scalar product. So the first method is if you know the magnitude of the two vectors, so the magnitude of A and the magnitude of B and the cosine of the angle between them. You can do the scalar product by multiplying the two magnitudes and then times cosine of the angle between them. The really important bit is this angle theta. So I've got it drawn in the picture here. Your angle theta is the angle between vectors A and B where they're drawn tail to tail. Okay, so that bit is really important. So A and B drawn tail to tail. And then theta is the smaller angle Because you could make a perfectly valid angle or a perfectly valid argument that the angle is this one out here. That's not the angle we use. We use the inside angle. So that angle theta is always between 0 and 180. Okay, so it's always the inside angle. So that's the important bit there. So you use this method when you know the magnitudes of the vectors and the angle between them. If instead you knew the components of the vectors, you would use this method. So you multiply the x components, multiply the y components, multiply the z components, you add those up, and it'll give you the same answer as you would get up here. So two methods for taking the scalar product. The two forms come from this basic definition of a scalar product. So if you have your unit vectors, I, j, and k, so the x, y, and z directions, I dot I, j dot j, and k dot k, those scalar products are all equal to 1. And then if you multiply two perpendicular ones like I dot j, when you have perpendicular ones, that scalar product is equal to 0. So you can use this method to figure out this result. I'm sort of expecting that you more or less know something about scalar product. In Physics 1050, you would have used it in thinking about work and power. I do have a review section up on Brightspace, and we're going to get some practice in class. So if you want some review, you can check that out, or if you want to come talk to me, we can do it in person as well. But I'll expect you to be able to do the things that I do in class with scalar product, so to follow along with what we do. And why don't we write down that answer, because this one is really important, is a scalar. Which means your answer would not have an I hat, a j hat, or a k hat. Lots of times it's easy to get confused because you've got so many vector things going on. Okay, so let's go ahead and think a little bit more about this dot product and scalar product and how it applies to electric flux. So I think everybody is okay with the idea that electric field is a vector. We've been working on that for a while, and your field is related to your force, which is also a vector. But the idea that area is a vector, that might be new to some people. Area is definitely a vector. The way we find an area vector is we say an area vector points straight out of the face. So if you have any sort of an object at all, let me say my coffee cup, if I wanted the area vector on the side, it would point straight out. Area vector on the bottom would point straight out. So your area vector is always perpendicular to the face. The way your book starts to draw area vectors, so area is a vector, we say yes. Your book defines first the normal vector for the surface. And in math speak, the word normal means perpendicular, just like normal forces were perpendicular to surfaces. So if we have a flat surface like this, your normal vector, your normal unit vector, would be a vector of length 1 that was perpendicular to the face sticking straight out. And then your area vector would be that same direction, and it would have a magnitude of the area of the face. So for this one, the area magnitude would be length times width, and the direction would be out of the face. So area is a vector. That answer is absolutely yes. The area vector is parallel to the normal unit vector. So that has length 1 and sticks straight out of the surface or perpendicular to the surface. So our area vector then is perpendicular to the surface. It points outward. And we'll have units of meters squared in general. Okay, so that's what we know about our area vector. So that's if we have a flat surface like this. What if we had a cylinder? A cylinder has a bunch of different faces. Area vectors will always be perpendicular to the face, so we'll get some different directions there. On the top of the surface, the unit vector sticks straight out. So the area vector would be perpendicular to that. On the side, straight out perpendicular, the area vector is parallel to that. And on the bottom, the unit vector sticks straight out from the bottom, and the area vector is parallel to that. Kind of get the idea? We'll be drawing a bunch of these area vectors as we go through. We can do it on a cube as well. So the normal unit vectors are straight out from every face. And the area vectors would be parallel to those. You calculate the magnitudes of the area using your high school geometry. Area of a rectangle is length times width, circle is pi r squared, things like that. Okay, good to hear. So that's how we draw the area vectors. Let's put electric field, area as a vector together, and let's do an example of calculating electric flux.
Okay, so the normal vector and the area vector are in the same direction?
Yeah, they're parallel. Yeah, always. So for our example, and why don't I give you a minute to try it first before I do the solution up on paper here. I've got a rectangular surface. I'm showing the normal unit vector. My electric field is up at this angle of 30 degrees to the horizontal. And you have to find the electric flux. As a hint, you know the magnitude of the electric field, you know the dimensions of your surface, so probably you could find the magnitude of the area. So maybe you want to use this expression to find the electric flux. You give it a try for a couple of minutes and then we'll do it together.
Assuming we should look at SI units for flux.
Oh yes, if I didn't mention the units for flux before, this is a great time to put them in. So flux is E dot A. So it will have units of newtons per coulomb times meters squared. So those would be your units there. Always best to work in those units. I guess technically you could write newtons per coulomb times centimeters squared, but these are the units we typically go for. Okay, so I think that maybe was enough time for everybody to give it a try. If you got an answer of 2.77, then you fell for my trick question. Okay, so there's a little bit of trick in this one. So let's go through what that little bit of a trick was. Our electric flux is E dot A. We've got the two forms. We'll use the one with magnitudes and angle. So magnitude of E times magnitude of A times the cosine of the angle between them. We know the magnitude of E is 320. Let's find the magnitude of A. The magnitude of A is equal to 10 centimeters, 0.1 meters times 0.1 meters, 10 by 10, to give us 0.01 meters squared. So that's what we put in for our A. Then theta can be the tricky bit, and you should definitely keep an eye out for this because it's easy to trip up. Theta is the angle between your vectors A and B. So A dot B is AB cos theta, where theta is on the inside. In our picture, E points up this way. There's E. Our area vector points straight up. There's our area vector A. This is the angle we want. This is theta. This is the angle we're given. Okay, so you gotta be really careful with those angles because they can really trip you up. Sometimes you're not given the angle you want. So our angle theta is gonna be 90 degrees, take away 30 degrees, equals 60 degrees. So now we can come back to our workings. 320 newtons per coulomb times 0.0100 meters squared times cosine 60 degrees to give us 1.60 newtons per coulomb times meters squared. Okay, so for anybody who saw through me and got 1.60, you deserve like 2 stars on your paper. Great job. Anybody who got 2.77, just 1 star. Okay, because you still use the right format. And then notice here, electric flux does not have any direction. There's no I, J, or K in this answer because this is a scalar. It is just a number, so no direction here. Big questions? So that's when we use magnitude and direction. Let's try and get one using the other form. So I'm going to leave that equation up on the top of the page. So we have a 2 centimeter by 3 centimeter rectangle lying in the XZ plane. So let's just label the sides of our rectangle. I'm going to call this one the 2 centimeter. I'm going to call this one the 3 centimeters. What is the magnitude of the electric flux through the rectangle if this is our electric field, and then for homework, if that's your electric field? So if we want to find our flux, we know we have to find the scalar product. We have 2 choices of form. The top one is if we know magnitudes and angles. We don't exactly know that here. We know more about the components. So yes, let's use the second form for calculating the flux this time. So our electric flux is E dot A equals EXAX plus EYAY plus EZAZ. Okay, so we'll have to get each of those components so we can multiply them and find our answer. Let's start with the components of our electric field. These are pretty straightforward because we just read them off the picture, off the given information. Our X component of electric field is the bit next to the I hat. EX is 100 newtons per coulomb. The Y component is the bit next to the J hat, minus 200 newtons per coulomb. The Z component is the bit next to the K hat. There is no K hat, so the Z component is 0. So there's our components of the electric field. We also want our components of the area vector. We're not exactly given that, but we can figure it out. So let's start with the direction of the area vector. So this is a rectangle. It's in the XZ plane, so it's lying flat. The direction of the normal unit vector is straight up out of the face. The area vector then is also straight up out of the face. So you see that's the same direction as the Y direction, so up is the Y direction. That means our area vector A is the magnitude of the area times the J hat. Yep.
Wouldn't the J component be positive considering the formula is, like for writing out vectors is always
Here?
minus J? Yeah, wouldn't it be positive considering it's
But it
always
gives
minus
negative
J?
right here.
Yeah, but I thought the formula for writing out vector notation was always I hat minus J hat plus K hat.
I think you're thinking about kind of determinants of a matrix.
Okay.
Like where you do this one times that one minus this one times that one?
Yeah.
Yeah,
But
I think maybe
thought
that's
that
what
was
you're thinking
always
of.
the formula for vector notation.
No, a generic vector, I'm gonna write this on a separate sheet of paper, like the generic form of any vector, so vector A is AX I hat plus AY J hat plus AZ K hat. All positives. These X, Y, and Z components can be negative in and of themselves, but they're always adding together. Okay, so let's keep going with finding our area. The magnitude of the area is going to be the length times the width because it's a rectangle. So the magnitude of the area is length times width, 0.02 meters times 0.03 meters equals 6 times 10 to the minus 4 meters squared. So our area vector is 6 times 10 to the minus 4 meters squared, pointing straight up, j hat. So for our components of the area vector then, it's only got the j hat, that means the x component is 0. The y component is 6 times 10 to the minus 4. It doesn't have a k hat, so the z component is also 0. Okay, so now we've got all of our components in a list. We can go ahead and sub them in here. So our net electric flux is EX times AX, that bit is 0, so 100 times 0 is just 0, plus EY times AY minus 200 times 6 times 10 to the minus 4 meters squared, plus EZ times AZ, 0 times 0 gives us 0. So our net electric flux is negative 0.120 newtons per coulomb meters squared. This question did ask for the magnitude of the electric flux, so there's just one step to do after this one. The magnitude needs the positive value. So positive 0.120. And here I'm just going to throw out a word of caution. Your book talks about the flux in and out of a surface. Be very careful there. Your book sort of talks in its language about flux having a direction, but flux does not have a direction. Flux is a scalar. It doesn't have a direction any more than temperature has a direction or mass has a direction. The only thing that the negative sign and the positive signs tell you about flux is whether the electric field lines go into a surface or out of a surface. And that's what the signs of flux mean when we have a closed surface. So I'll just caution you when you're reading your book, even though the book seems to talk about flux having a direction, it does not have a direction. It's a scalar. Flux can't point in or out because it doesn't have a direction, just like temperature can't point in or out or up or down. So careful there when you're doing your reading. Okay, I'll leave part B for homework. It'll follow the same method. I don't think that one will be too tricky for you. Okay, and now we're going to come back to our point charges. Yeah.
Yeah, does the area always only have a y component?
No, area doesn't have to have only a y component, and actually we're sort of going to get to this next. In one of the homework questions, you see it's tilted at an angle, so area could be in any direction. Yes, good question. So for this question, we're going to try and calculate the electric flux around a positive point charge. We already know lots of things around a positive point charge. That's why we're going to use this to calculate the electric flux. When we get to the end of calculating the flux, we're gonna take a careful look at our answer and see what that tells us. So this slide here, this one's gonna carry a lot of weight, it's gonna do a lot of stuff. So we'd like to calculate the electric flux through a spherical Gaussian surface of radius r centered on the charge. The first thing we're gonna do is we're gonna draw our Gaussian surface. So our Gaussian surface, I'm drawing the 2D version, which means I'm drawing a circle. If you wish to imagine it, really this should be a sphere. Typically, you're gonna draw a Gaussian surface with a dashed line. So I'm gonna label it my picture of Gaussian surface. You should always label your Gaussian surfaces so that you're clear about what they are. It's a sphere with radius r. I'm going to label that radius in my picture. So radius will be from the charge to the surface of the sphere, radius r. What else do we know here? We know the electric field around a positive point charge is K times Q over R squared. This was one of the first results we talked about when we did electric fields. You may not remember that K was what we called our Coulomb's constant, and you could break it down as 1 over 4 pi epsilon naught, where epsilon naught was your permittivity of free space. So that's a way of writing down what K is. And the direction of electric field around a positive point charge is out from the point charge. So this epsilon naught is 8.85 times 10 to the minus 12 Coulomb squared over Newton's meter squared. So that's a constant that we know. So we know the electric field. We've picked our Gaussian surface, and we'd like to calculate the electric flux. So we'll start by writing down the expression for the electric flux. Our equation for our electric flux is the scalar product between the electric field and the area vector. Okay, so we'll start right from the beginning. When we have the electric field dotted with the area vector, two ways to calculate your scalar product. You can use components or magnitudes and angle. It makes sense to use magnitudes and angle here because we know the magnitude of the field. We can figure out the magnitude of the area of the surface. So we'll do E times A times cosine theta. Okay, we want to be able to fill something in for each of those values. Let's deal with the theta before we go any further. So theta is the angle between the electric field vector and the area vector when they're drawn tail to tail. Our electric field vector is already drawn for us. So that's already drawn in our picture. Our area vector, remember, points straight out of the surface. So the normal unit vector will point straight outwards. Here's the normal unit vector. And the area vector also points straight out. It's parallel to the normal vector. So your electric field points straight out, your area points straight out. So in this expression, both of these vectors are outwards. That means that those vectors are parallel. If they're parallel, it means that theta equals 0. And cosine of 0 is equal to 1. Everybody good there? So let's keep going. So that leaves us with E times A times 1 is E times A. So this is the electric field. This is the area of the Gaussian surface. I'll come down to a new line just because I ran out of space. So then my electric flux is going to be the magnitude of my electric field. I'm going to use 1 over 4 pi epsilon naught rather than K times Q divided by R squared. So that gives me the magnitude of the electric field at a distance R from the point charge. That's how we calculate electric fields near a point charge. So that's the E bit. I'm multiplying by the A bit. Here's where you have to brush off your high school geometry. The area of a sphere is 4 pi R squared. Sometimes these are results I would give you on a formula sheet. Sometimes I wouldn't. I kind of expect you to know those basic geometry ones. So there's the area, or there's the electric field times the area of the Gaussian surface, 4 pi r squared. Let's see what we get here from this equation. I've got a 4 in the numerator, 4 in the denominator, pi in numerator and denominator, r squared in numerator and denominator. So all those things cancel out. And I'm left with the electric flux around a spherical point charge is the charge divided by epsilon naught. Okay, so this is kind of a big result. I know this is written in the wording, but I'll just write it down here again. So the flux through a sphere with radius r centered on positive point charge q. So something's interesting to notice about this, or something interesting. Our Gaussian surface had a radius of r, but our expression for our flux doesn't have an r in it, right? That's kind of interesting. So we might ask, is that very meaningful, or what does that tell us? And is there anything else we can learn from thinking about this? So we're going to think about this for a little bit. And we're working our way towards creating Gauss's law. Any questions here? Yep.
I'm just curious about the electric field in the area. Does the area always have to like close to the electric field? Because you could pick an area vector at any point on that surface. For example, it could be anti-parallel. So would that affect like the angle?
So you're always talking about them kind of when they're in the same place. Yeah. So both outwards. And that would reduce to Gauss's law. The general form is given in an integral format, and when you do the integral, you kind of take the sum over all the same bits, but we're staying away from the integral form. It's a good, insightful question, though. So let's think about this for a little bit.
So if we were given a question asking when the field or when the vibe would be at its maximum, we just said whenever it's parallel to the area vector.
Yeah, it's whenever the electric field and the area are parallel.
Yeah, and we could just state that then as our answer. If we were-
Probably throw the equation in as well. Yeah. So we're going to ask about the result that we just got. Let's just write that down again at the top of the page. So we said that around our point charge, our electric flux was E dot A, and it turned out to be Q divided by epsilon naught. So we're going to ask some questions about that result. And as we ask, let's remember what electric flux tells us. It gives us the measure of the number of electric field lines penetrating a surface. That's what electric field is. Number of electric field lines through a surface. So, question 1. Does the electric flux depend on the size of the Gaussian surface? Okay, so why don't we take a poll? Who thinks yes, it should depend? Who thinks no, it should not depend? Okay, looks like the no's are the loudest vote here. Let's justify why that's so, using our understanding of what electric flux means. So for our first picture, so does it depend on the size? I'm going to draw two Gaussian surfaces of different sizes. So my first one is going to have radius r1. Please imagine that that's spherical. My second one is going to have radius r2. The number of lines cutting through surface r1 is 8. So 8 lines through surface r1. depend through surface R2, also 8 lines. So regardless of the size of the Gaussian surface, you have the same number of electric field lines penetrating the surface. If you have the same number of lines, you have the same electric flux, because that's what electric flux measures. So does the size depend? The answer is no, because you get the same number of electric field lines. Okay, what about the shape of the Gaussian surface? Do we think that matters?
Yes.
Okay, well, mixed answers here. Okay, this is good. Let's see about that one. So let's draw two Gaussian surfaces again. Here's my first surface. I've got 8 lines penetrating through this surface. So that's a sphere. And then to go with my sphere, I'll also draw a cube. How many lines through the cube? Also 8.
Yeah, but if you put a plane there,
Yeah, like a triangle or something.
Okay, so when we do this, our Gaussian surface does have to be a closed surface. Okay, so it definitely has to be closed.
Like a cylinder?
Like what?
A cylinder?
Like a cylinder could work as well. So a Gaussian surface, this was back in our original definition, is a closed surface. We did some calculation of flux through planes. Those planes weren't Gaussian surfaces. Gaussian surfaces are always closed. Okay, so does it depend on the shape of the Gaussian surface? Turns out that's a no. Does it depend on the location of the charge inside? So we had our charge at the center. Did it have to be at the center? Okay, I heard one lukewarm no. No confident answers. 2 lukewarm no's. Okay, so let's have a look at this one. So I'll draw my first surface centered about the charge. There's my first one, 8 lines. I'm going to draw a second surface not centered about the charge. Still 8 lines. So the answer there is no. And this is reflected in the equation. This equation has got Q over epsilon naught, doesn't say anything about the size, doesn't say anything about the shape, and it doesn't say anything about the position. So our results match our equation. Any questions to here? Turns out this word in my question is really important. I'm going to highlight that one. It turns out that bit is really important. So it doesn't matter where the charge is inside, but it turns out it does actually have to be inside. So we're going to deal with the inside bit next. Okay, so we're good to keep going? And if anybody is keeping track, I've asked this on a midterm or a final exam at least a couple of times.
So the
Yeah.
flux does not depend upon the geometry of the shape
Exactly.
or the size
Right.
or the location.
As long as it's inside. Yeah. So if I say it has to be inside the surface, the first question I ask is, well, what if it's outside? Okay, so that's a good question. Let's think about what happens if it is outside the surface. So what if the charge is outside? So there's my point charge here. I know what electric field lines look like around a positive point charge. I'm going to draw those electric field lines. So there are my electric field lines around my positive point charge. And this little bizarre shape I got Word to draw for me, that's my Gaussian surface. And this is a closed surface. So our net electric flux, our total electric flux, would be the number of lines leaving the surface, take away the number of lines going in. So we always want to find the total electric flux. We've done it really simply before, we just had lines going out. So our total flux is the number of lines that go out, subtract the number of lines that go in. So I'm going to trace over my surface here. And let's ask about the net flux through this surface. So through this surface, I have one line in, one line out, one line in, one out, one in, one out. Okay, so looking at this picture, we see that every line going in also comes back out. So let's think about why that's the case. If we remember what we know about electric field lines can start on a positive, so they can start on a positive and go outwards, or they can stop on a negative. I've got a positive charge right here. The only way to get my field lines to stop inside the surface is if there's a charge inside the surface, but there's no charge inside the surface because all the charge is outside the surface. So I can't have any lines starting inside because there's no charge inside. I can't have any lines stopping inside because there's no charge inside. Therefore, every line that goes in has to come right back out because I can't start inside and I can't stop inside. Okay, so everything that goes in also has to come out. So that means if we have a closed surface with no charge inside, the net electric flux is going to have to be 0. So this is a slightly new notation, Q enclosed. Okay, and this is what I'll be using from now on. So capital Q, sometimes a lowercase, with ENCL meaning enclosed. And this means enclosed by the Gaussian surface or inside the Gaussian surface. If Q enclosed is equal to 0, it means no lines start or stop inside the surface. That means every line that goes in also comes out. Which tells us that the net flux is 0. Okay, so the total electric flux can only come from charges inside. That's the only way to have a flux, is to have a charge inside the surface. Okay, questions? I was really hoping we were going to be able to put this together with the other stuff and get Gauss's law. But there's only 2 minutes and I definitely don't want to keep you over time. So we'll just finish this idea on Friday.